What's up guys, another video on rates. We're going to look at ways in which we can determine the rates and sort of what differences in graph we might get as we go through. So before we get into it, please like, subscribe, share with anyone you think will be interested. Yeah, really looking to grow the channel, get to as many people as possible. Let's get into it. So we've got three main different methods of determining the rate of reaction. So for starters here, we've got sort of the disappearing cross method, right? So often we've got some sort of reaction that creates an opaque liquid, right? So this becomes opaque. So essentially, we can see the cross here, but over time it will disappear. We'll put all of our reactants in, we'll start the timer, and we'll stop the timer as soon as this cross has disappeared. What we can then do is we can repeat this. So here we're going to repeat this method for various things to work out what's going on. Now, often here, rate is directly proportional to 1 over time. So here, we're going to record the time it takes for this to disappear. So we might have our different concentrations, for example, or our different temperatures, and we're measuring the time here. So say if we've got 0.1, 0.2, etc., etc., and we're going to measure our different times. And then to work out our rates, we do 1 over time, again, because that is directly proportional to the time, right? Next, here, we're going to have our initial mass, we're going to add our magnesium, and again we're going to start the time. So this is like a continuous monitoring method, because what we're going to do is we're going to have our whatever concentration, whatever surface area, whatever temperature, etc., and then we're going to record our mass at preset times. So we might have in seconds, 0, 20, 40, 60, 80, etc. And we'll measure the mass. So we might start off on 180 here and then move to 178, 176, etc., etc., etc. And we might well plot the change in mass, right? Now, the reason why this is happening is because as our magnesium reacts with the hydrochloric acids, hydrogen gas is produced, right? So we've got this reaction plus 2HCl makes H2 plus MgCl2. So because this is a gas, this is now being released and our mass is changing, right? Now, the way our graph is often going to look here is we're going to start off with our high mass. We might record mass here, and our graph might look something like this. And we draw tangents like so to work out what our rates are at any given time. Now, that's something we're going to look at a little bit more when it comes to year 13 stuff. It becomes much more important when we're working out orders of reaction. Don't worry about that. That's coming later. Next, let's say this is the same reaction. So we've got our magnesium, our hydrochloric acid, again, hydrogen gas is being produced. This time, we're collecting that hydrogen gas. So this little plunger, this gas syringe will start here, and then gradually as hydrogen is produced, this plunger will come out, right? And again, we're going to record at various different times to see what that might look like. This time, our graph's going to look something like this. So let's say this is what we're using. We're using, again, this continuous rate method, and we're going to draw what a graph might look like. We're not too worried about the numbers within this graph as of yet, but we'll get into this bit now. So, number one, we've got a small piece of magnesium. Again, the mass will always be the same here. We've got a concentration of 2 moles per decimeter cubed of hydrochloric acid, volume of 50, temperature 20. This is, again, not exact, but it's a general idea as to what these graphs might look like. So, we're always going to have this kind of shape. let me make this thicker so you can see it properly. This kind of shape, right? Where we, perfect, come up to something like that. So what's happening is here, our concentration starts off high, where our rate starts off high because our concentrations are at their highest there, and as the reactants get used up, the rate of reaction gets smaller and smaller and smaller until we get to 0, right? This is where the reaction has completely stopped, yeah? Now let's see what number 2 would look like. So we'll have a little key here. Let's use a different colour. Okay, so here, let's see what our change is. We've got the same size piece. Our concentration is halved, but our volume has doubled. So if we're thinking about CNV, if our concentration is halved, but our volume is doubled, our moles is going to stay the same, right? So our amount of product is going to remain unchanged, but our concentration is halved. So as we saw last video, that's going to reduce the rates. But because you've got the same number of moles, we're going to produce the same amount. So we need to show this by making sure that our line is less steep, but it gets to the same point. So let's try that. So again, our line is less steep, but it gets to the same point. Perfect. Next. Here. Now we've got large pieces. So remember, if we've got large pieces, more of our particles are sort of hidden, if you like. So there are going to be less collisions and so slower rates of reaction, right? We're assuming that we've got the same mass here, that's controlled. Now, our concentration is the same as in number 1. Our volume is the same as in number 1. Our temperature is the same as in number 1. So, everything else is the same, except our surface area is now lower, which means the only things we need to worry about is our line is less steep than this first one, but again, we've got the same amount of product. So again, you should use a different colour. Let's have a little key here. So here, again, this could be either side of this line. We haven't got enough information to know whether it's going to be steeper or shallower than that. I'm just going to do it in between the two. Again, up to the same point and across. Nice. Next. Okay, number 4. Now we're back to small. So let's compare to 1 again. Our concentration's doubled. Our volume is the same. Our temperature is the same. So the only thing we need to worry about here is our concentration. Again, if we think about CNV, our volume has stayed the same, but our concentration has doubled. Therefore, our moles will double as well, which means our amount of product will double. So we can see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we're going to finish up there, right? We're going to be quite quick, but we're going to finish up there. So we're going to show this line as steeper than the others. Nice. And then levelling off at the top. Perfect. So I would like you to try those last 3. I'll answer those at the end of next video. Please screenshot this, give it a go. Now on to what we did last time. So here, let's start thinking about our answers to these questions. So this is always our structure, right? Our factors, particles, collisions, and rates. So we're constantly thinking about making sure we include all of these within our answer. So, first one. Clearly, concentration has changed from 1 to 2. So we've got an increase in concentration. Therefore, more particles per unit volume, let's say dm cubed, per dm cubed, more collisions, faster rates. Nice. Solid ground down to a powder. We've looked at that a little bit this video again. So you should know that we've got an increase in surface area, more exposed particles, more collisions, faster rates. Temperature. Again, let's think about including all of these. So we've got higher temperature, obviously, higher kinetic energy for those particles. All of them have higher kinetic energy. More collisions, also higher force of those collisions. Therefore, more with at least the activation energy. Therefore, some much higher rates. And last one, catalyst removed. This structure falls down a little bit for catalyst removed, but we can just about use it. So no catalyst. But I was going to say higher activation energy. Less collisions have the activation energy. Therefore lower rates. Hope that's helpful. Give the previous questions a go. We'll answer them then. We'll look at the Maxwell-Boltzmann distributions next time. Maybe an unfamiliar term, maybe not. We'll get into it. Until then, happy revising, guys.